Welcome to the online video lecture series for intermediate algebra. This is section 2-2, where we will be covering graphs of functions. My name is Dr. Scott Franklin. I'll be leading you through this lecture. In this section, we're going to be talking about how we graph functions using points, by plotting specific points. This will be very similar to the technique that was used to graph equations back in an earlier section, and if you're not familiar with graphing, you'll want to go back and rewatch from section 1.3, where we introduced the rectangular coordinate system and the T-chart or value table method for graphing equations. We're going to use the exact same technique, only now using our function notation and our function concepts. We're also going to talk about the vertical line test and how it might be used to identify functions. We're going to also interpret graphs of functions and be able to identify the domain and range of a function simply by looking at its graph. Whenever we're given a function, say for example like this that we see in the example down below, g of x is equal to 2x minus 3, or we might be given a function of f of x or whatever variables may be involved. If we want to graph that function, we want to draw a picture that represents that function, what we're really going to be doing is we're going to graph or plot the set of all points where x is your input and your second coordinate, your y coordinate or height of your point, is the output of your function. So instead of graphing x comma y, where y is a variable in your equation, we're now graphing x comma f of x, where x is your input, f of x is your output. So for each value of x, the height of the curve over that x is given by f of x, or is given by the value of the function. And what I recommend is the same strategy or technique that we used in section 1.3 when we first covered how to graph equations, and it's the T-chart or the value table method. So if you're given g of x is equal to 2x minus 3, what you want to start by doing is building a table where your first column is your x and your second column is your g of x. And then pick several values for x, plug them in, and see what you get out, and plot those as points, and then we'll connect those points together with a smooth curve. So let's say x, let's do our usual choices that we used back in the earlier section. This gives us a good range of x's to start with. So if my coordinate system looks like this, what I'm really doing is I'm looking at, for these values of x here, -1, -2, -3, and then 1, 2, and 3, I'm asking from this table, what are the heights of the curves for each of these values of x? So if I plug in -3, what do I get when I find g of -3? I will get that by plugging -3 in for x, just as we were doing when we introduced function notation. And so 2 times -3 is equal to -6 minus 3, or -9. What that tells me is the point above or below -3 has a height of -9. So -9 means negative. I'm going to go down 1, 2, 3, 4, 5, 6, 7, 8, 9. So roughly it right there is that first point. Now I'll plug in -2. What is g of -2? Remember that we get that by plugging -2 in for x. So 2 times -2 minus 3 is -4 minus 3, or -7. -7. So at -2 I have a height of -7, which is right there. 1, 2, 3, 4, 5, 6, 7. There's my height. If I do g of -1, I'm going to be 2 times -1 minus 3 gives me a -2 minus 3, or -5. -1, -5 is right there. Then I'll come over and do g of 0. I'm going to need to use some scratch space here. I'm going to do the same thing over here. This is my scratch work. What's g of 0? That's 2 times 0 minus 3, so that gives me a minus 3. Because 2 times 0 is 0, minus 3 makes minus 3. So at x equals 0, I'm down 3 right there. G of 1 will be 2 times 1 minus 3, or 2 minus 3, which is negative 1. Right here. G of 2 would be 2 times 2 minus 3, or 4 minus 3, which is 1. So at 2, I'm at a height of 1. And what do you begin to see the shape of this? This looks like a straight line of points, and that's in fact what it is. G of 3 would be 2 times 3 minus 3, or 6 minus 3, which is 3. Alright, so 3, and then a height of 3 plots right there. So that turns out to be, let's try that again, a line that passes through those points. Okay. Now, normally I would draw this with either a straight edge, or I would draw it with my pen to illustrate that curve. But in the homework that you'll be doing, if you do this homework online, the interface allows you to be able to plot these points as a way of answering this question. Okay, so that's how we graph a function, is we just graph the inputs and the corresponding outputs as points. It's important to point out at this point that not all graphs will represent functions, because if you go back and remember, the key idea to a function is that one output gives you, say that again. The key concept of a function is that one input gives you exactly one output. Okay? Now, as we've seen from graphing this, the graph is for function says that for every x, the height of the curve above it is the output. Okay? So if I had a curve, like here's my coordinate system, and my curve does this. Okay? That means at any point here, if I were to call that x, the height of that point right there is f of x. If x was over here, then same thing. That height right there would be the function, right? F of x. So for no matter where I go, if I go here, or if I go here, if I go way over here, or somewhere back over here, there is exactly one height that corresponds with each of those x values, each input that I have on the x-axis. However, what happens if you have a curve that does, say, this? Here's your x-axis, here's your y-axis. What is the output for that x? Well, notice there are two of them, which means not a function. So the easiest way to tell by looking at a graph whether to determine whether or not it's a function is to see, are there any places where you have more than one output for any input? That is, if you ever draw a vertical line, does it ever intersect more than one place? And if it does, then that turns out not to be a function. Let me restate that formally, and we'll call this the vertical line test for functions. And it says the following: if any vertical line intersects, it's an R, intersects the graph in more than one point, then the graph does not define y as a function of x. So if it hits it more than once anywhere you draw a vertical line, then it's not a function. So what you have to have for a function is that no matter where you draw a vertical line, it only hits it once. Okay, so like look at these three examples, A, B, and C here. Notice no matter where I draw a vertical line on this, how many places is it intersecting that curve? There's only one every single time, right? So that would be an example of a function. Same thing on the next one. No matter where I draw the vertical line, right? Whether here, 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 any of these places, how many places is it intersecting each time? And the answer is 1, so it's a function. However, on the next one, you can see if I drew a vertical line here, all's well. But if I drew it right here, notice the number of points that I intersect. Boom, boom, boom. Okay, there's the problem. If it happens at least once, it's not a function. I'll use the abbreviation FN for function. Okay, that's how we applied the vertical line test. It is important at this point that I make a note about some of the ways that your textbook and your online homework will draw graphs so that you can obtain certain information from the graphs. In some pictures you may see a closed dot at the end of a line, and anytime you see a closed dot at the end of a line segment like that, that means that the graph does not extend beyond this point and that the point belongs to the graph. It's included. Okay, so this point actually means that the output at x is equal to 2 is 2. Right? So if this is y is equal to f of x, this means f of 2 has what height? So if I go to x2, the height right there is 2. So f of 2 is 2. On the other hand, if you have an open dot, that means that the graph does not extend beyond that point, like you have a circle right there, and that the point does not belong to the graph, which means that f of negative 3 for this graph is undefined. Even though it looks like there's a height there, because it's open, we're saying that that function does not have an output for negative 3. You may also, in some cases, see an arrow, which is what's drawn here at the end of this. And the arrow indicates that the graph extends indefinitely in the direction in which the arrow points. The function f of x, which is given by the formula negative 0.016x squared plus 0.93x plus 85, is a model. And it models the average number of paid vacation days each year for full-time workers at a medium to large U.S. company after X years. So if you've worked there X years, the output f of x is the number of paid vacation days that you'll receive. Now this illustrates one of the reasons why it is so useful to have a graph, because in many cases you can see what happens over time. In this case, time, because your x-axis represents how many years you've worked there. And you'll see that the number of years that you work the number of paid vacation days that you receive increases. Right? It doesn't increase at a constant rate. It begins to slow down, and as you work there longer and longer, the increase from year to year is less and less. Okay, but one of the advantages of a graph is also you can go through and just estimate some values. Instead of actually plugging them in the formula, say we didn't have the formula or we just want to eyeball this, what is an estimate for f of 10? First of all, what does f of 10 mean? F of 10 is the output when you plug in 10 for x. So x being the number of years you work there, that says after 10 years, the output would be how many days of paid vacation leave do you expect or do you receive? So I'm going to go to x equals 10, here's the x-axis, and look at the height of this. Okay? Which appears to me to be around 16. So I would say a reasonable estimate for that is that f of 10 is approximately 16. Curly equal signs just mean approximately. So that's my answer, 16 days. The second question here is it's an inverse question. Instead of asking us how many paid vacation leave days do we receive after a given number of years, we are asked how long before I get 20 days of paid vacation leave. When does the function value, when does the height equal 20? Okay, so I'm going to go to a height of 20, boom, and look at when that hits, and I want to know what's the x that gives me that height, which looks a little bit past halfway, so I would guess that's around 18. So I would say the answer to that question is x is equal to 18 years. It would take 18 years before you reach 20 paid vacation days. One last note or item that we can cover when we're looking at the graphs of a function is to be able to identify, just from looking at it, what's the domain and range of the function. Remember, if you go back to what we covered when we first introduced the concept of functions in the earlier lecture video of 2-1, we saw that the domain of a function is its set of inputs. It's all the x values that you can plug in. So when you look at each of these graphs, what you're looking at is what are all the x values that correspond with a height. They correspond with a point above it or below it. The range, on the other hand, is the set of all outputs. And since the output on a graph is the height of the graph, you're then asking for the range. That's going to be the set of all numbers that have a height of the curve at that particular height, that have a point on the curve that has that height. So in looking at this, the correct domain on part A would be that it's the set of all the x's, and notice it's the x's that start here and go all the way up to here. Okay? So that would be an x that's bigger than or equal to, because there's a closed dot here, -2, and less than or equal to +1. That is your set of inputs, or your domain. Your range, on the other hand, would be r is equal to the set of all, and I'm going to call them y's because that represents the y-axis, and it's the y's that start at, now what's the lowest height? The lowest height is 0, and the highest place the curve reaches, boom, is a height of 3. And again, because there's closed dots at the ends, then I'm going to put or equal to. So that's the set of all y's, where y is between 0 and 3 inclusive. Alright, so the domain on the second one is the set of all x's over which there is a curve, so from here to here, but there is an open dot on the left-hand side, which means that the domain is going to be the set of all x that starts at -2. That's the leftmost value that has a curve point over it, but it's not included because of the fact that there's an open dot there. But it's everything bigger than it, right? So even like -1.999 is in this set. It's a number that has a curve over it. But exactly at -2 does not. But then we go all the way up to +1 and including +1 because there is a closed dot at the right end. The range is the set of all y such that, now where is y? Y is, the lowest value of y is down here at -1, and it's included because there's a dot that has a height of -1. And then the highest it goes up to is 2, so less than 2. Okay, last one. The domain of this set is the set of all x, and by looking at this graph, what I see is that every point from here all the way up to 2, notice even though there's an open dot right here, there's a closed dot that does have a height corresponding to it. Same thing here, that has a closed dot. So everything but not including this end has a point on the curve or on that graph above it. So I would say that x goes from -3 inclusive up to 0 not inclusive. The range, on the other hand, is what are all the possible heights that I have on this thing. Okay, well notice I have a height here, but I actually don't have any heights in between -3 and -2, or any heights in between -2 and -1. I only have 3 distinct heights, not even a range. So I wouldn't write it as an interval like this, or I wouldn't write it as an inequality. In fact, all I'm going to say is that the range is -3, -2, and -1. Those are the only 3 heights that we have an output for. Alright, so that's how we can look at the picture of a graph and determine what the domain and the range for that graph will be. And that's the end of section 2-2.